In our previous class, we discussed about a different type of stretching and bending vibrations and the factors affecting those vibrations. Today we will discuss about the different type of vibrations present in different type of functional groups, how these functional groups behave when they are subjected to infrared photon or infrared irradiations, and what kind of informations we can obtain from the IR spectrum. Before discussing that, this particular slide, I have told you earlier that this particular slide will tell you about different type of peaks. For example, this is your strong peak, this is your medium, and this one is your weak peak. And similarly, what other information we can take from different type of IR spectrum. This is if these are some sp3cs stretching vibration, sp2ch stretching vibration. These are the different type of fundamental vibrations or their wave number at which they particular will appear. Now particularly we are concerned with this IR absorption range. This is the IR absorption range, and this will tell you about different type of the functional groups and different type of the other groups they will absorb at this particular region. For example, this is the region, this is called as the fingerprint region, in which a different type of vibrations will happen. And this is is called as the functional group region. Means from 1400 to 600 we have fingerprint region, and from 1400 to 4000 centimeter inverse we have functional group region, in which different type of functional stretching vibrations will happen. And here different type of vibration will happen, and this is called as the fingerprint region. What is the benefit of this particular fingerprint region is that we know that every one has a different fingerprint. Similarly, every molecule will have a different fingerprint, and that fingerprint will not resemble to different or to other kind of molecules. So if we could not able to find any information from this particular reason, we can find out various information from this particular fingerprint region, and we can identify a particular structure, and this will help in the structure elucidation of the organic compound. So this is the IR spectrum that is particularly divided into two categories. One is the fingerprint region, and the second one is the functional group region. Now what is this particular fingerprint region, if I am particularly concerned? So this is your fingerprint region, 600 to 1400 centimeters. It is called as the fingerprint region, and this is normally a complex area showing many bands and frequently overlapping each other. This particular complexity limits its use to the fingerprint and should be ignored by beginners when analyzing the spectrum. As a student, you should focus only on the analysis of the rest of the spectrum. Means if you are particularly concerned, you should focus on this particular area, and this is the functional group region where the different type of functional group absorb. And this is the fingerprint region. It is as written here, that is particularly complex, and the more advanced chemists generally use this region to identify the molecule, identify the different type of molecule, right? Structure elucidate can be done on the basis of this one. Now we are particularly talking about different type of the functional groups. So starting from the first one, and the first one in this category is the alkanes. Now alkane will contain carbon-carbon single bond, and that will also contain the carbon-hydrogen single bond. Now what kind of vibrations a alkane molecule can show? So if I am particularly talking about alkane, it can have four different type of vibrations. And what are these four different vibrations? It include the CH stretching vibration, CH bending vibration, carbon-carbon stretching vibration, and carbon-carbon bending vibration will be here. It means in case of alkane we will have four different type of the vibrations, which will include the carbon-hydrogen stretching, the carbon-hydrogen bending, carbon-carbon stretching, and carbon-carbon bending vibration. Now we will see it. For example, this is symmetrical stretching, and this is asymmetrical stretching. Means stretching can be done in two ways, either symmetrically or asymmetrically. You can see by these values that your asymmetrical stretching vibration will always be at higher wavelength as comparison to the symmetrical stretching, so it will absorb slightly at higher wave number as comparison to symmetrical stretching. Similarly, this is in case of methylene group, if this is particularly the cases that this different type of vibration is there, symmetrical and asymmetrical stretching vibration here. Now this is your methyl group, and this is another different type of carbon hydrogen is here, wagging and twisting is here, rocking and scissoring vibration is also here, and you can see the different values of these asymmetrical stretchings. This is symmetrical stretching, and this is twisting, this is wagging, this is scissoring just like scissor, and this is your rocking deformation in bending vibration. What kind of information we can obtain? For example, this is particularly a IR spectrum of n-hexane just containing 6 carbon atom in the carbon chain, and here this particular these two peaks. Otherwise you also having these are the very weak peaks, so these are not considered here. We are particularly concerned with these peaks. So this particular peak at this above 1400 region is due to the carbon hydrogen bending vibration here, and this particular peaks is because of the carbon hydrogen stretching vibration. So on the basis of these information we can say that this particular spectrum belong to n-hexane. Similarly, we come to the alkenes. In case of alkenes, what will have, it may have carbon double bond, and it may have carbon hydrogen single bond. So what kind of vibrations it can have? It can either have carbon double bond stretching vibration, it can have carbon hydrogen stretching, right? And in plane and out of plane bending of the CH bond is also there. So if we are particularly concerned about this carbon double bond stretching vibration, so it will come at to be 1667 to 1600 centimeter inverse, and it is moderate to very weak. It may also happen carbon double bond stretching if I am particularly talking about. This is these are the different type of the for example, this is your CS2 double bond CS2, and this is the alkene where one of the hydrogen is replaced with one of the R group, and then we replace 2 hydrogen with the R group. Now we have replaced again 2 hydrogen. Now the relationship between this and this is, this one is trans, this one is cis, and this one is trans, and similarly we have replaced a third hydrogen as well, and in this it is completely substituted alkene. So if we are going from this one, that it will absorb at 1600 centimeter inverse, it will absorb at 1640 centimeters, that it will go on increasing. It means when in case of alkene we particularly when we go to more substituted alkene, the value will increases, and this generally increase in the value, maybe because of the coupling interactions and coupled vibration. Because of that one, you can see that this is because of that kind of interaction inside that alkene molecule. So this is the case that this is the least substituted alkene, this is the CS2 double bond CS2, and this is the highly substituted alkene in which all the 4 hydrogen has been replaced with 4 R groups. Now we will come to one more case. I want to tell you that this is your cis isomer. It will a little bit absorb at 1650 centimeter inverse, and this is your trans, and this will absorb at somewhat higher value as comparison to the cis isomer. Similarly, we are having this one, it may be medium, it may be weak, and this will tell you about the intensity of the peak that will be absorbed in case of the IR spectrum. Lack of symmetry, and because of the absorb more strongly. I have told you earlier that cis and trans, they have different absorption peaks, and this is because of the symmetry of the molecule, right? Now, what is the effect of conjugation? For example, we are talking about alkene. At that time, we may have dienes. Different type of double bonds will be there, and those double bonds and dienes, it may be either isolated dienes, it may be cumulative dienes, and it may be conjugated dienes. So, what will be the effect of that conjugation? For example, here you can see that this is the only alkene, and will absorb at 1670 centimeter inverse, and this is a diene in which the double bond are present in the conjugation. And in case of conjugation, what will happen? It will absorb at the lower wave number it is particularly absorbing. And what is the reason behind that? It lower the force constant. How it will lower the force constant? It can lower the force constant because of the resonance. The bond that is present, that will acquire a partly single bond character, and because of that one, generally single bond character will lower down the force constant value, and because of that one the frequency will be at lower as comparison to higher wave number. So this is one is for alkene carbon carbon multiple bond. If we are particularly concerned about this one, blue color, this carbon hydrogen stretching vibration I am particularly talking about. So this will absorb at around 3000 centimeter inverse in maybe 3000 centimeter inverse will result from aromatic acetylenic or olefinic C-H stretching vibration. So we may have different type of this one is your scissoring vibration. This may be out of plane bending vibration, in which we have twisting and we have wagging. Like this one is your twisting and this one is your wagging. So different values are here. For example, this one is 1000 to 650 centimeter inverse, and it will have 1416 centimeter inverse. So if we are particularly concerned about this stretching vibration normally appear at around 3000 centimeter inverse or more than that one. And if we are particularly concerned about CH bending vibration, it will absorb at lower wave number. It either may absorb at the fingerprint region as well. For example, this is a particular IR spectrum of this is cis2 octene, and this one is 1 hexane. In case of this one, this particular 1660 centimeter inverse is because of carbon carbon double bond stretching vibration. And this one in case of alkene, this is CH stretching vibration is here. In case of CS stretching vibration, still it is present in here. And this one is because of the double bond C olefinic carbon is here, which is sp2 hybridized, and this carbon when connected to the hydrogen, it will have stretching vibration. And this large peak is because of the double bond CH stretching vibration. Now if we are particularly concerned about this one, one hexene is here and double bond character is here. So again this one is sp2 hybridized carbon, and this is attached to the hydrogen. So this is stretching vibration, and it will appear at 3080 centimeter inverse. And this is in case of alkane, it will have CH stretching vibration, so it will appear here. Now this is carbon carbon double bond stretching vibration, and this will appear at 1642 centimeter inverse. And this is CH bending vibration, which appears at still lower frequency as comparison to these different groups. So this is in case of the alkenes. Now what will happen in case of alkynes? This is alkyne will have carbon carbon triple bond, and because of the carbon carbon triple bond, it will absorb generally at 2100 centimeter inverse. And when it will absorb at 2100, so it will have carbon triple bond carbon vibration will have. And other than this, it will have carbon hydrogen single bond is also there. And one case it will have that triple bonded carbon which is attached to the hydrogen, it will also have that vibrational frequency as well. Now through example we will discuss about this one. For example, this is the IR spectrum of 1 octane. In case of 1 octane, this is your carbon triple bond carbon stretching vibration, and this is the exact wave number at which this particular carbon carbon triple bond, that is this is sp hybridized carbon and this is again sp hybridized carbon, so it will absorb at 2119 centimeter inverse. This is carbon triple bond carbon stretching vibration. Now we will have triple bond carbon, and that triple bonded carbon is attached to the hydrogen, so that will also have a stretching vibration. And this stretching vibration will particularly appear at 3313. It means this will appear higher as comparison to alkynes. In case of alkyne, alkene, the double bond carbon hydrogen stretching vibration was appeared at 3000 to 3100 centimeter inverse, but here it is appeared at more than 3300 centimeter inverse. So this is the case in case of alkyne. This is your carbon triple bond carbon stretching, and this stretching is particularly because of triple bonded carbon and hydrogen stretching vibration, and this vibration is because of the carbon hydrogen which was in case of alkane. This is because of the carbon hydrogen stretching vibration, right? And this is because fingerprint region is here, and this is another evidence that will from this basis we can also identify the structure of the compound. Now this is your 4-octane we are particularly concerned. Now there is no carbon hydrogen stretching vibration. We can identify this one. Why these two examples have been given here, that is, here you are having triple bonded carbon and that carbon is attached with the hydrogen, and here you are having triple bonded carbon only attached to one another, and there is no hydrogen attached to these two triply bonded carbon. So we are not having any kind of peak in this area, but in above case we are having a peak that will be because of this triple bond carbon hydrogen. So here you will have stretching is also not visible because of lower intensity of this particular not presence of the hydrogen. No carbon triple bond stretching is also visible here, because it will only be visible in case if there is hydrogen, at that time it will be visible. So this is also not visible in that case. In that case we can have only the alkane, means the carbon which is sp3 hybridized. That carbon when attached to the hydrogen will have only that peak, right? So we can differentiate between alkane and alkyne on the basis of the IR spectrum. In tomorrow's class we will discuss about the aromatic compound. Now we will compare that this is particularly IR spectrum for in case of alkyne, and if we are particularly concerned that this is the IR spectrum of the alkenes, in which we are having that here you are having carbon double bond carbon stretching vibration is here, and here you are not having this is carbon double bond carbon stretching vibration, which is a very sharp peak appear at here. Here you are having double bond carbon hydrogen stretching. Here you are also having carbon hydrogen stretching vibration. And in case of alkane, for example, we are particularly concerned about this one. This is your carbon hydrogen stretching, and this is your carbon hydrogen bending. So in case of alkene we will have this carbon hydrogen stretching and carbon hydrogen bending at higher intensity, and in case of alkenes we will have carbon double bond carbon stretching vibration along with this bending vibration, this stretching vibration, and a more stretching vibration appear at here, and this carbon multiple bond carbon will appear at here. And similarly in case of alkyne we will have one additional peak here, we will have one additional peak here for carbon triple bond carbon stretching, and this will for triply bonded carbon hydrogen stretching vibration. So on the basis of this IR spectrum we can easily identify that whether it is alkene or it is alkyne. Tomorrow we will discuss something about aromatic compounds and their functional groups.